Hi, I'm Enrico Palma and I'm going to talk about black phosphorus, or also known as phosphorene, as complementary metal oxide semiconductors. In today's world, everything has gone expensive. Laptops, smartphones, and even tablets are priced highly due to their high demand and low supply. Metals that are used in producing the IC chips for these electronic gadgets have been depleting ever since the discovery of these devices. The next big thing in electronic devices is to make them flexible and lighter, as most of these applications are targeted towards printable electronic devices. Silicon is abundant, but it is expensive and not lightweight. But what if there is a material that is cheap, abundant, lightweight, and easily produced? Presenting phosphorene, one of the hot topics lately in the material world. But before we go dive into the material, let us go behind the science of semiconductors and transistors. Semiconductors contain both electrons and electron holes. These particles are divided by the depletion layer, which serves as a barrier to the electron from the n-type to the p-type. You can think of this as an electric switch, wherein applying voltage allows the electron to flow from one area to the next. This concept happens when you consider the electron flowing as the on state and electrons not flowing as the off state. Put this concept into a CMOS chip inside the computer, the on state will be read as 1 and the off state will be read as 0. Sounds familiar? But wait! The challenge of ICs today is to fit in more transistors in a single unit of IC. This is predicted by Moore's law, which states that the number of transistors in a single IC doubles every 2 years. This becomes problematic as more and more transistors are fitted, the chance of quantum effects to occur becomes more evident. Quantum effects such as tunneling happens when you try to squeeze in more transistors. Tunneling allows the electrons to bypass the depletion layer without any form of signal. This becomes problematic as the CMOS chip cannot identify whether it is a 1 or a 0. This means that several errors appear as the memory of the device may not be able to handle the instantaneous switching of states. Going back to phosphorene, we try to see whether it can compete with the main star of transistors, silicon. According to Korean scientists from Sunkyun Kwon University, phosphorene is lighter and has a very high theoretical carrier mobility. It means that the electron flow is high enough to process information at higher rates. Another feature of phosphorene is that it has a tunable bandgap. It means that it is possible to make a p-type, n-type, and ambivalent types using the same material. This is done through playing with the thickness of phosphorene at its atomic layer. This is somewhat better than silicon, as silicon requires doping to be either p-type or n-type. It is also lighter than silicon as the dopants increase the weight of the device. It also reduces production cost, as increasing or decreasing the thickness of the material eliminates the cost of further processing, which involve doping other foreign elements. Here in the Philippines, there's a great avenue with dealing or even handling CMOS chips that utilizes phosphorene. We know that the Philippines is one of the world's largest and active users of social media such as Facebook and Instagram. This tells us that in our country alone, almost everyone uses a computer just to get connected with one another. This fact alone can serve as a motivation to set up industries that focus on building chips that cater to the internet needs of users in the country. This can potentially boost and innovate existing structures in the country. How? We can now teach more children how to use a computer. We can now provide more internet services in the local setting through internet cafes. We can now even utilize the computer to reach the needs of the people from sensational media headings to important political issues. A possible solution to the problem earlier is reflected in a patent by Chinese researchers producing a method yielding high conversion rates in making phosphorene. Key findings in this patent include that it has a 97% conversion rate at low temperatures and pressures. This means that it is industrially capable of mass production. It also is non-toxic and requires no catalyst. This may somehow boost the industry of electronics as the demand for lighter and more flexible electronics will arrive sooner or later. This means that phosphorene may end up as the next big thing alongside graphene and stannine in the world of electronic devices. Thank you.